All right, hi everyone, and welcome to another Win Neuro seminar. Today we're very happy to host Ya'ara Yeshurun from Tel Aviv University. Ya'ara did her PhD with Noam Sobel and Yedidu Dai at the Weizmann Institute, focusing on unique aspects of olfactory memory. And she then completed her postdoc with Uri Hasson at Princeton University, focusing on the neural correlates of interpretation of naturalistic stimuli. And she is now joined the School of Psychological Sciences as a faculty member at Tel Aviv University. And she's going to talk to us today about really cool work about how humans are acting in the wild. So I'll just give you a little reminder about the control features of Crowdcast. So on your right, you have a chat where you can ask any question. No question is too stupid for the chat. I'll be monitoring that chat. So if there are any clarification questions, please use that and I'll refer them to Ya'ara. If you have any deeper questions or questions that are maybe for more discussion, that are more suitable for the end of the talk, please use the Ask a Question button at the bottom of the screen, and you can also vote on questions there. And at the end of the talk, we'll refer the top voted questions to Ya'ara. I will invite you to the screen to ask your question unless you ask me not to. So if you don't want to be asked to the screen, please mention that in your question. Cool. So with that, Ya'ara, we're really happy to have you here today. And the floor is yours.
Thank you. Thank you, Alon, and thank you, Avital, for the invitation. I'm really excited to virtually be here. And today I'm going to talk about brain mechanisms underlying shared understanding. And I would like to start the talk with a quote that I like by Henry David Thoreau. So he said, "It's not what you look at that matters, it's what you see." And even when we're looking at this picture, although we will all agree, sorry, do you see the screen?
Not now. I see you. You need to do share screen.
Okay. So, wait, I'm sorry. In a second.
You just need to hover with the mouse above your face and then you can do the screen. There we go.
Yes. Okay.
Good.
Okay, so now I think things will be more comprehensive. So today I'm going to talk about brain mechanisms underlying shared understanding. And I would like to start with a quote by Henry David Thoreau that said, "It's not what you look at that matters, it's what you see." And when we're looking at this picture, we will all agree that we're looking at a political debate between Donald Trump and Hillary Clinton. However, two different people might actually see very different things. And this is the case because individuals perceive the world through their own subjective filters, their emotions, their beliefs, their prior knowledge. And in our lab, we're interested in asking on which level do these filters operate. So, for example, when a left-wing and a right-wing person are watching at the same political debate, where does the response diverge? Is it already in the curriculum that the aim differs? They're just not looking at the same thing? Is it in early sensory regions, in higher order regions? Is there a gradient in the amplification of the response such that there's a small difference in early sensory regions, which is amplified in higher order regions? So today I'm going to present to you 3 projects aiming to test this. The first project.
Ya'ara, I'm going to stop a sec because your audio is a bit crackly for me, and I think for. So I'm wondering if it might be better if you try a headset, even though when we tested before it was okay, but now it sounds not.
Yeah, I'll try just a second. Is this better?
Let's try to talk a bit.
Okay, so today I'm going to present to you 3 different projects. The first project is we presented participants. No? Yes?
It's still a bit muffled, and it doesn't feel like it's much. I'm not sure. If there's nothing to do about it, then we'll continue like this. But for some reason, it's a bit muffled.
I wonder if there's something about the settings that I can change in crowd.
Are you sure these headsets are plugged in? Because it sounded like it didn't really change when you plugged it in.
They are, but I have another set, so just a second.
Okay, sorry. I can't hear you yet. You might need to unmute yourself if you hover above your face and try to press on the microphone. Let's see, I'm going to kick you out and invite you again back to the screen, okay?
Hi.
That's much better.
Oh, cool.
Yes.
Okay. I wonder what happened.
Yeah, I don't know. Okay, great. Yeah, perfect. Okay. Go ahead.
Oh, so should I start?
Yeah, I think start from the beginning and share your slides.
Okay, that's a good idea to share my slides. Just again, share screen. Okay.
Perfect.
So now you can see and hear me?
Yes, excellent.
Okay, great. Okay, so I would like to start again with a quote that I like by Henry David Thoreau. So he said, "It's not what you look at that matters, it's what you see." And when we're looking at this picture, while we all agree that we're seeing here a political debate between Donald Trump and Hillary Clinton, 2 different individuals might actually see very different things. And this is the case because we perceive the world through our own subjective filters, our emotions, our beliefs, our prior knowledge. And in our lab, we're interested in testing, in asking, on which level do these filters operate? So, for example, when a left-wing and a right-wing person are watching this political debate, where does their response diverge? Is it already in the retina that the response differs? So it's just that they're not looking at the same thing? Is it in early sensory regions, in higher order regions? Is there a gradient in the divergence of the response such that there is a small difference in early sensory regions that is amplified in higher order regions? So today I want to discuss 3 different projects. 3 different projects that that aims to address this question using fMRI. In the first project, we presented participants with stories that are composed of similar words, but they generated different narratives. In the second project, we manipulated participants to interpret the exact same situation in different ways. And in the third ongoing project, we use participants' natural subjective filters. Now, the two first projects were done during my postdoc in collaboration with Uri Hassan in Princeton. And the third project, the ongoing project, is conducted in my new lab in Tel Aviv University. So let's dive into the first project. Oftentimes, a small change in the words we use can generate a large difference in the narrative. So for example, and this is an example that I gave at November 2016 during SFN, which was a few days after Trump was elected. So I can say, he built a wall. They did not pay for it. A big surprise. And I can also say, she built a wall. They did not vote for her. A big surprise. And by changing only 3 out of 13 words, I generated a very different narrative. And the question is how the brain translates small difference in the input into a big difference in the narrative. And to answer this question, I would first like to introduce to you the concept of processing timescales hierarchy. So this concept was developed based on many different studies in Uri Hassan's lab. And the idea is that all cortical circuits can accumulate information over time. And the timescale of accumulation varies from from regions that have short processing timescales of tens to hundreds milliseconds, which is equivalent to articulation of a phoneme or a word, to regions that have medium processing timescales, which is a few seconds, which is equivalent to a few words or a sentence, to regions that have long processing timescales that accumulate information over many seconds or many minutes, that is equivalent to a few sentences or a paragraph. So the processing timescale hierarchy predicts that the longer the processing timescale of a voxel in the brain, the larger the difference between the two narratives that I presented. So if we go back to the example, between he built a wall to she built a wall. So voxels that accumulate information over short processing timescales that is equivalent to a word, they will have a relatively small difference in their response, as only 3 out of the 13 words are different between these two paragraphs. However, voxels that accumulate information over a sentence will have a larger difference because 2 out of 3 of the sentences here are different. And voxels that accumulate information over long processing timescales, over a paragraph, will have a relatively large change in their response. So the hypothesis is that small changes in the response of short timescales regions will be amplified as it goes along the processing hierarchy. To test this hypothesis, 36 participants were lying in the MRI scanner while they listened to 2 stories that had the exact same structure. Only 33% of the words were changed. So the first story started like this. Let me know if you can hear it.
Not so well. So maybe it's better if you.
Okay. So it doesn't really matter. It was read by the same actor. And the Milky Way story starts like this. The situation seemed almost hopeless, and after he spent most of the last weeks drinking, he knew he must confront the truth. The vodka story started like this. The situation seemed too good, and after she spent most of her last weeks worrying, she knew she could enjoy the moment. Okay, so by changing 33% of the words and leaving the structure exactly the same, we generated 2 different narratives. In the first one, Thomas recently broke up with his girlfriend, Emily, but he was still obsessed with her. After meeting a hypnotist, this is replaced by a fixation on Milky Way, and there is a happy ending. In the second story, the vodka story, Rachel reaches the final of American Idol, and she's obsessed with the judge, Simon. after meeting a psychic, this is replaced by fixation on vodka, and there's a sad ending. So now, what we wanted to do is first to find the brain response, the region in the brain that process the narrative. So for that, we used intersubject correlation. I will give a brief explanation about this method, intersubject correlation. This method was developed more than 15 years ago by Uri Hassan during his PhD in the Weizmann Institute. And the idea is this. So while in the standard neuroimaging paradigms, what we do, we compare different conditions within an individual. So for example, if we're interested in regions that are involved in processing faces, we'll compare between a face and a house, and we will find regions that are involved in processing faces. However, in the intersubject correlation, we switch the paradigms such that we compare different individuals that are perceiving the same condition. And the advantage of this method is that it allows you not to have a control stimuli, as each participant brain serves as a design matrix to predict the brain response of the other participants. So this allows you to use more natural and longer stimuli, such as movies and stories. And these movies and stories usually have the richness and complexity of events in real life. And what we do is we measure, we assume that by finding brain response that is shared across participants that are watching the same stimuli, it will allow us to find the dynamics of the response to this stimuli. So what we do, this is an example. For example, this is one listener that is listening to a short story, and this is the response in the auditory cortex, and this is the response of the auditory cortex in a second listener, and we just find the correlation between these two, and we do it for each and every subject. So, for example, what you see here are 5 listeners, and this is their response during rest. And you can see that when the story starts, you can see that the response starts to be aligned. So during rest, there is no correlation between the brain response of different participants, but when the story starts, the response becomes aligned. So I used the intersubject correlation to find similarities between people that listen to the vodka story and people that listen to the milky story. But now I was also interested in finding and testing for differences between the brain response to the 2 stories. So for that, we developed a method that is based on the Euclidean distance. So for each voxel in the brain, or for each ROI, we extracted the time courses of the 18 participants that listened to the Milky Way story. We did the same thing to the participants that listened to the vodka story. And then we calculated the mean response of the Milky Way story in this specific voxel and the mean response of the vodka story in the same voxel. We then calculated the Euclidean distance between these 2 time courses, between these 2 vectors. So this resulted in 1 Euclidean distance value for each of the voxels that were involved in processing the story. We then rated these voxels and divided them into 5 beans, from beings that had relatively small difference in the brain response to beings that had relatively large difference in the brain response. And next, we wanted to see where these beings are located in the brain. And this is what you see here. So the brighter colors are regions that had relatively small difference in the brain response, and darker colors are regions that had relatively large difference in the brain response. And what you can see here is, for example, primary auditory cortex had relatively small difference in the response between the Milky Way story and the vodka story. However, when you go up to higher order regions, you can see that the difference become larger and larger. And just to give you an estimation, so for example, the difference in the left TPJ, the difference in the neural response between the two stories could be more than 10 times than the difference in the auditory cortex. So now we wanted to test our hypothesis that this amplification, the difference in the neural response will be correlated with the processing timescale hierarchy. So for that, we used an independent data set that was collected in 2011 by Julia Lerner in Hassan's lab. And what you see here is the brighter colors are voxels that had short processing timescales that accumulate information over short processing timescales. And the darker colors are voxels that had relatively large, long processing timescales. And what you see here is the map that I've just showed you of the distance in the neural response between the two stories, between the Milky Way and the vodka. And just by looking at it, at these two independent data sets, you can see that there is a striking similarity between the difference between the stories and the processing timescales. And indeed, we can see here that there was a strong positive correlation in which the longer the processing timescale of a region, the larger the difference between the two stories. Okay, so now we got this amplification map, and when we compare the response across the whole story. Next, we wanted to test whether it's a specific part, specific scene in the story that generated this amplification map, or is it true for the whole story? So for that, the author of the story divided the story into 12 scenes. And we just, for each scene, we rank the difference in the neural response between the two stories. And for example, here, when you see in scene 1 that it goes from lighter colors to darker colors, so you can see that it's the same order as we got for the whole story. And it was also true for the second scene. And in fact, this was true for 11 out of the 12 scenes. And only in the last scene, there was a small change in the ranking of the amplification. So you can see that this amplification map that we got from early sensory regions to higher order regions holds true for the majority of the story. Finally, we wanted to test whether, so what we saw is that when we create a small change in the words we use, we saw that this change was amplified from early sensory to higher order regions. But maybe any change it will do will generate this same amplification map. So for that, we generated another control stimuli, which was Milky Way synonyms. So for example, if between the Milky Way to vodka story, what we change is the situation seemed almost hopeless, and after he spent most of the last week drinking, he knew he must confront the truth. In vodka, we changed it to the situation seemed too good, and after she spent most of the last week's worrying, she knew she could enjoy the moment. So in the Milky Way synonyms, we changed the exact same number of words, but this time to a synonym, so the narrative did not change. So we changed it, for example, instead of almost hopeless to desperate, instead of he to Martin, instead of he knew he must confront the truth, he knew it was time to face reality. And now the question is, if this amplification of difference is dependent on forming distinct narratives. And the answer is yes. So this is what we saw, this amplification map, when we compared between two different narratives, between the Milky Way and the vodka story. And this is what we got when we compared between two similar narratives, between the Milky Way and the Milky Way synonyms. Also, we got the positive correlation, when we compared between the two different narratives, we got a positive correlation between the processing timescale index of a region and the distance in the neural response between the two stories. However, we did not see it for the difference between the Milky Way and the Milky Way synonyms. And in fact, we can see here that if anything, it's the opposite direction. And we can see that these regions, these dots that are voxels that are located in the early auditory cortex actually had the biggest difference in between the Milky Way and the Milky Way synonyms. And I think it's interesting because when you think about it, so for the auditory cortex, the difference between he and she, as was the difference between Milky Way and vodka, is not that big. However, for the higher order regions that generate the narrative, the difference between he and she is quite large. However, for the auditory cortex, the difference between he and Martin is quite big because the stimulus properties, the sound properties are different. However, for the higher order regions, it's exactly the same, as he and Martin refers to the same person. So to summarize this project, we asked how the brain translates small difference in the input into big differences in the narrative. And we suggest that local change in the input structure is amplified along the processing timescale hierarchy to create a big change in the meaning. Now, in this project, we used two different stories that varied in some of the words. In the next project, what we wanted to do is to test how interpretation changed the brain response to the exact same stimulus. So for that, we had 40 participants that they listened to a short story by J.D. Salinger, Pretty Mouse and Green My Eyes. This story is about a phone conversation between two good friends. One of them came back from a party without finding his wife, Joni, and he's calling. This is Arthur, this is Lee. So Arthur is calling Lee to ask him if he knows anything about Joni's whereabouts. Now, we manipulated participants' interpretation of the story by presenting them with one of two different contexts. So in the cheating context, participants listened to the story while thinking that actually Arthur's wife is cheating on him with his best friend, Lee. In the other 20 participants listened to the story after being exposed to the paranoia context, in which we told them that actually Arthur is always paranoid, he's always thinking that his wife is cheating on him, and it's not true. And Lee is with his girlfriend and just desperate to go to sleep. They do not know anything about Joni's whereabouts, about Arthur's wife whereabouts. Okay, so to give you an impression of the effect of the context on the story, I want you to, and after they listened to the story, outside the scanner, they filled in a story comprehension questionnaire. So now I want you to listen to part of the story. I hope it will work, but if not, I will just read it to you.
No, unfortunately not. Doesn't work.
Okay. So you won't hear the gifted actor that read it. So I will read it to you. Okay, so Arthur is saying, did you happen to notice when Joni was leaving? Did you happen to notice if she left with the Ellenbogans by any chance? The gray-haired man looked left again, but had this time, away from the girl who was watching him, rather like a young blue-eyed Irish policeman. No, I didn't, Arthur. Didn't she leave with you? No, Christ, no. You didn't see her leave at all then? Well, no, as a matter of fact, I didn't, Arthur. Okay, so I'm sure that if you would listen to the actor reading this, it will be much clearer, but the idea is that the context, the cheating or the paranoia context, really shaped how you interpret this this story based on, for example, in the cheating context, you're sure that Lee is lying because you know that the girl next to him is actually Arthur's girlfriend, however, Arthur's wife. And in the paranoia context, you're just assuming that he really doesn't know anything about where his wife is. And let's see how our participants comprehend the story. So we had 27 context-independent questions, such as what was the girl doing when the phone rang? And what we saw is that there was most of the participants knew the correct answer. There was high performance, and it was comparable between the two groups. However, we also had context-dependent questions, such as why do you think Lee didn't want Arthur to come over? So in this case, participants that were exposed to the cheating context will say because he didn't want him to find out that his wife is there, whereas participants that were exposed to the paranoia context will say because he was desperate to go to sleep. And indeed, that is what we saw, that participants that listened to the story after being exposed to the cheating context had much more cheating-appropriate responses, and participants that listened to the story after being exposed to the paranoia context had much more paranoia-appropriate responses. So it's nice, our manipulation worked. And now we wanted to test for brain response that differed according to the context that the participants were exposed to. So for that, we developed a Euclidean distance classifier. What we did is in each voxel, and you can do it also in each ROI, we extracted the 20 participants' time courses. So 19 participants served as the training set, and we left one out that served as the testing set. Sorry. So we also did this for the 20 paranoia participants. So this is a two-leave-out algorithm. And we then calculated the mean response of the cheating training set, the mean response of the paranoia training set, and then we just calculated the Euclidean distance, the cheating Euclidean distance between the time course of the testing set to the mean response of the cheating training set. We also did this between the time course of the testing set, the response of the testing set, to the mean response of the paranoia training set. And if the cheating Euclidean distance was smaller than the paranoia Euclidean distance, the classifier classified the participants as being exposed to the cheating context. And if the opposite, so it classified it as being exposed to the paranoia context, and we also did it to the second subject. And we repeated this 400 times, each time taking 2 participants out of these 40 participants. And then we average this number into 1 classification accuracy per voxel. The next thing we wanted to test is whether this classification accuracy is significant or not. And for that, we did the exact same thing, only we shuffled the labels to create 2 pseudo groups that in each group, we had some of the participants were exposed to the cheating context and some of the participants were exposed to the paranoia context. And we then tried to classify the pseudo groups. We repeated this 100,000 times to generate a null distribution of the classification accuracy. And then we tested where the real data classification falls in this null distribution. So let's see. What we see here is a map of voxels that had context-dependent response. So these are voxels that the classifier was accurate in classifying whether they listened to the story after being exposed to the cheating context or to the paranoia context, and the classifier accuracy ranged between 66 to 88% in classifying this. And what we see here is that these regions that are mainly part of the default mode network or the mentalizing network or the narrative comprehension network. So these regions had context-dependent response. And what's the thing that is new about this is that the vast majority of studies that define this narrative comprehension network, they tested the response between a narrative that is comprehensible to a narrative that is not comprehensible. But in this case, what we see is that it's not just 1 or 0. These voxels, this network, is sensitive to two different narratives, to two different interpretations of the same narrative. So you comprehend, in both cases you comprehend, you just generate in your head a different narrative out of the words that you're presented with. A second interesting thing that we can say here is that most of these regions that had context-dependent response are actually voxels that have long processing timescale. They accumulate information over a long time of many seconds or many minutes. Okay, so it's nice. We see that we have that these voxels had context-dependent response. And the next thing we wanted to ask is whether there's a correlation between difference in interpretation and difference in the neural response. So what we did for testing this is we had 5 independent raters rate the difference in the mental states of the characters on a scale of 1 to 5. So this is a hard task. So it's I call it a second-order theory of mind task. So these raters had to think about a participant that is exposed to the cheating context and a participant that is exposed to the paranoia context, and they listen to the story, and what will be the difference between these two listeners. So this is what you see here. The y-axis is interpretation difference, and the x-axis is time, and you can see that the difference in the interpretation varied along the story. So it's not that the context changed the whole story, but it had a different effect on different intervals of the story. And for example, in this case, where you see the raters have that there's a big difference in the response, what happened in the story there was that Arthur told Lee that Joni just came home. And if one was exposed to the cheating context, they know that Arthur is just saying it to save his face. And if you were exposed to the paranoia context, you're happy that everything goes back to place and everybody can go to sleep. Okay? So there was a variable difference in the interpretation of the story, and we can calculate the difference in the neuron response for each, like we did in the Milky Way and vodka stories in the first project. We can calculate it for each segment of the story. And what you see here, the x-axis are voxels that had context-dependent response. The y-axis is time, and the darkness of the dot represent the difference between the listeners, the two contexts, between listeners that were exposed to the story after the cheating context and listeners that were exposed to the story after the paranoia context. So what we wanted is just to correlate this interpretation difference vector with the response difference in each of these voxels to test for voxels that had interpretation dependent response. And this is what you see here. So in white and blue, the white are all the voxels that had context-dependent response, and in blue is out of these voxels that had context-dependent response, the voxels that had significant correlation between difference in the neural response and difference in the interpretation. Meaning that all these voxels, the larger the difference in interpretation between the two groups, the larger the difference in the neural response between these two groups. So to recap, we asked how prior views and beliefs shape the brain response to a narrative. And we found that although the external input was exactly the same, so it was 12 minutes of a story that were exactly the same, there was a difference in the neural response, and mostly in the mentalizing and narrative comprehension network that depended on participants' interpretation. Now, these results demonstrate that 4 lines of context that were presented in the beginning of the story, before participants started listening to the story, were enough to generate this in-group clustering, out-group differentiation of the neural response. And you can imagine that in real life, when people constantly accumulate information through different sources, so it could be news channels with opposing political views, so this difference might be even larger. This in-group clustering, out-group differentiation of the neural response might be even bigger. So you can imagine how it will be in real life, or we can move to the next project. So the next project, which is an ongoing project due to many reasons that are not, I'm not responsible for, is the elections 2019, 2020 in Israel. So a few months after I started my position in Tel Aviv University, elections were declared in Israel. And I then thought it's a unique opportunity to test how people's natural tendency to interpret situations through their own subjective filters shape the neural response in real time. So the idea was that the elections will change the interpretation of some of the political events that happened before the elections. And by testing the brain response of participants with opposing political views, both before and after the elections, this will enable us to test for how subjective filters shape the brain response both between individuals and within individuals on 2 different time points. So what we did during 3 weeks before the elections, we scanned 40 participants. 20 participants were left-wing and 20 were right-wing. And then we're watching 8 different movie clips in the MR scanner. The movie clips varied, and there were mainly political campaign ads. So we had some left-wing political campaign ads, and we had also right-wing political campaign ads. This is in Hebrew, but the idea is that it advocates a certain party. And the participants were lying in the MR scanner. They watched each of the movie clips, and after each movie clip, they were presented in the scanner with 3 different questions. So one was, how much did you agree with the main message? The second was, how much did this clip interest you? And this third was, how emotionally engaged did you feel? And they answer it in the scanner with a mouse on a visual analog scale from not at all to very. After the scan, we also had a detailed interpretation questionnaire on each of these movie clips to assess participants' reactions to the clips and their political views. Then we waited for the elections to take place. It was in April 9th, 2019. Then we waited for the coalition to be formed before we scanned them again. It didn't happen. So we decided to scan them again during July 2019. So this time only 24 out of the 40 participants came back, and they watched the exact same 8 movie clips again. Okay, they did the exact same task of rating inside the scanner and also a questionnaire outside the scanner. It so happened that we had another election in September 17th. We waited for the coalition to be formed. It didn't happen. We had another election in March 2020. the coalition has been formed, but due to COVID-19, we're still waiting to find the right time to scan participants, which is not, we're not sure when it will happen. Yeah. So this paradigm allows us to test two different things. So it allows us to test for differences in the brain response that stems from participants' political views, and it also allows us to test the dynamics of the brain response over time, while there are shifts in participants' knowledge and emotional responses following the elections. And as I said, for a couple of reasons, this is an ongoing experiment. And now I'm going to show you very preliminary results from this project. And it's going to be only from the first round in March, April 2019. So let's start with the behavioral results in the MRI scanner. So I remind you, we had 3 questions after each movie clip. How much did you agree with the main message? How much did this clip interest you? And how emotionally engaged did you feel? So first, let's look at the right-wing campaign ad. And what we can see here, in red are left-wing participants, and in blue, this is right-wing participants. And you can see that there was a big difference in how much they agreed with the main message in the right-wing political campaign ad. However, both groups were interested by this movie clip, and both groups were emotionally engaged with it. And we can see the exact opposite pattern for the left-wing campaign ad, where you can see that left-wing participants largely agreed with the main message, and right-wing did not. However, both groups were interested and emotionally engaged with the movie clips. In terms of the behavioral results that we gathered after the scan, so we had, for example, what I'm showing now is for the right-wing political ad, the Likud political campaign ad. So we had 5 filter-independent questions, such as, is it argued in the video that unemployment is at an all-time low? And participants had to say yes or no. And for these 5 filters-independent questions, you can see that there was no difference in the performance between the 2 groups. However, we also had filter-dependent questions, such as, to what extent do you believe that the legal proceedings will prove that Benjamin Netanyahu is innocent? Between not at all and very. And you can imagine that there was a difference between the 2 groups. And what you see here is the average response for these 8 filter-dependent questions. And there is a big difference in how they view what happened in the movie clip. Okay. So now let's look at the, again, very preliminary brain data results. So first, let's see, when participants were looking at, were watching the right-wing political campaign ad, this is the intersubject correlation, the brain response that processed this movie clip in the left-wing participants, and this is the brain response in the right-wing participant. Now we can see that there are many overlapping regions, but we were interested in testing for differences between the 2 groups. So for that, we used 2 methods. One method was just a t-test between the intersubject correlation value between these 2 groups. And the other method was the classification method that I described for the Salinger story. And let's look at it. So what you see here, these are voxels that had a significant difference in the intersubject correlation value between the 2 groups. In blue are voxels that were more, the response there was more synchronized in the right wing participants than in the left wing participants. Okay, and what you see here are many different regions, and for example, also here in early visual cortex, that was more synchronized in the right wing participants than in the left wing participants. And in general, we see that if we found a significant difference in the inter-subject correlation value, it was almost always to the directions that the right wing participants were more synchronized than the left wing participants. And we can see that, so this was for the right-wing political campaign ad, and we can see very similar pattern of response where if there was a significant difference in the inter-subject correlation between the two groups, it was the right-wing participants had more synchronized response than the left-wing participants. And here we can also see a high inter-subject correlation in the insula, for example. In the insula of the right-wing participants when they're watching the left-wing campaign ad. The next, the second method we use to, so this method reveals voxels or regions that are more synchronized. But next, we wanted to ask, okay, we want to look at regions that are involved in processing the stimuli in both groups of participants, but just that the response of these regions is different. So for that, we use the Euclidean distance classifier that I described before, and this is what we found. So this is for the right-wing campaign ad, and you can see here that, for example, that precuneus had a different response to the exact same campaign ad depending on the political opinions of the participants. I think more interestingly, because this we also found in the Salinger story, but what we found here is that also primary auditory cortex had a different response to the exact same movie, the exact same sound, depending on participants' political views. And we saw this for the right-wing political ad, and we saw a very similar thing for the left-wing political ad. So now, when I want to summarize this talk and this project by presenting again the question that we asked. So we asked, on which level do subjective filters operate? And when you look at the second project, the Salinger story project, you can see that when we manipulated participants to interpret a certain situation in a certain way, mainly higher order regions differentiate between the two groups of participants. However, when the filter, the participants came with the filter from home, I mean, it's much more rooted in their life, their political views. So we saw the difference in the neural response already in sensory regions. And with that, I would like to finish to thank Uri Hassan, which was a great collaborator and mentor during my postdoc at Princeton University, and to thank my lab and all the people that were involved in this challenging elections project and never-ending elections project, and mainly Naka Tabi that is bravely leading this. And thank you.
Great, thanks very much for an excellent talk. It's a never-ending election project for the entire.
For all of us.
Yeah. Cool. So we have a few questions. So I'm just going to invite some people to the screen. So Shraga, I'm inviting you now, and you can ask a question. You can also decline, and I can ask a question for you if you want. It always takes a second.
Okay. Should I stop my share screen?
Yeah, maybe. And then if you want to go back to
Okay.
show some stuff, you can share it again. Yeah.
Sure.
Yeah. There you go. Shraga is a Vital.
Yes, my pseudonym. Hey, Yara, thank you. It was
Hi.
a great talk. I really
Thank
enjoyed
you.
it.
Thank
And
you.
I was wondering about the Salinger project. So I was wondering whether you measured the level of empathy evoked by each of the narratives. So could it be that these areas that we know that have a lot to do with our level of empathy, so if there are different levels of empathy between the two narratives, would we find differences in the inter-subject connectivity? And also whether the level of a participant's empathy would predict the level of correlation between his signal and the group signal.
So that's a great question. We did not measure empathy. What we did, okay, so I have, so we did measure how much they identified and empathized with a certain character, but not at different time points. And the data we have is not, so for example, the difference in interpretation is a second order difference, right? So, yeah. I mean, it's different people than the one that were scanned. So I can't answer this with this data set. I can say that the Salinger story somehow, I don't know why, but somehow many different groups are working on it. And so I know that there's something about empathy, and a group in Princeton that is working on it and are trying to do real-time change in interpretation and make people interpret the Salinger story in different ways based on their brain response. But in terms, I think it's a great question, but we don't have the data for it.
Sure.
Yeah.
Thank you.
Thank you.
Cool. So the next question, it's my question. So about the election project, when you split, have you also controlled for other factors that tend to split the political map, like social economic status or like ethnicity or like origin in Israel or
okay, I think in Israel it's a bit, okay, I don't want to go.
Yeah, it's a slightly like I don't know, like tender topic, but yeah. there are general lines by which the political map is
right. So in general, I can say that we had what?
Education like level.
So okay, so I want to say that we had a lot of trouble finding right-wing participants in Tel Aviv University. And we tried many things, and we tried from different universities that are more known to be right-wing. And it was harder to recruit them. And that's why I think, so for sure, the right-wing participants were more heterogeneous from the left-wing participants. But that's why it's even more surprising that their brain response was more synchronized. But all of them, in terms of your question about socioeconomic status, so yeah, it's equated. But still, there's some of them were religious, for example, whereas all the left-wing participants were secular. So there is there's much more heterogeneity in the right-wing participants, and that's why I'm even more surprised from this.
Yeah. Cool.
Yeah.
Okay, thanks.
Yeah, sure.
Cool. So the next question is from Camille. I've invited you to the screen. It works, yeah.
Hi, thank you for the presentation. It was very interesting. I just have a question about the functional connectivity within the brain areas, and whether, I mean, we saw that there was in your areas of interest like significant difference between the two. So I'm talking about the election project. I wanted to know if you would be eventually interested, or if you already have undertaken the project for investigating the functional connectivity between these areas. If there's any, maybe the fact of seeing the videos from opposite wings triggered, I'm thinking, I don't know, amygdala, insula first, and then went to higher order areas. Not sure, again, but I wanted to know if you were interested in this.
Yeah, so this is a great question. I want to emphasize that what I did till now is inter-subject correlation and not functional connectivity.
Yeah.
But what I want to do, functional connectivity could be really interesting here. And there's also a relatively new method that was also developed in Uri Hassan's lab, that it's called ISFC. I recommend just looking at it. It's the idea is the same as inter-subject correlation, only looking at functional connectivity.
Right.
But we do want to do what you suggested about functional connectivity, but we also want to do, and we're now at the middle of doing it, so to kind of combine between the two first projects that I told you about. So now look exactly like you said, whether there's a small difference, for example, in the auditory cortex or the visual cortex, that is amplified in different higher order regions. And for now, I cannot say anything because we're still waiting for the statistics.
Yeah, of course.
But it looks like it's in the right direction. But I have to say that we were surprised to find such a that the classifier had such a high accuracy value in the auditory cortex, because it's the same input. And also what I wanted to say, don't remember. I think I had another thing to say, but I don't remember it right now.
No worries.
Okay.
Thank you.
Okay, thanks. So the next question is from Andrew. I'll ask for him. So in project 3, how does one determine right from left wing? Is being ultra right or ultra left affect the outcome rather than just more moderate levels of right or left?
That's a really good question, which I cannot answer, because as I said, elections were declared in Israel 3 months after I started. And when I heard about it, I said, okay, so we'll have a group of right wing, left wing, right wing that are secular, left wing that are Arabs, and we have I thought to have the whole Israeli population represented in this experiment. It was too much, and that's why we had to try and concentrate as much as we can on relatively homogeneous population. So all the left wings that we have are part, they voted for a specific party in Israel, Meretz, if anybody is familiar with the party, and we know how much they are on a scale of 1 to 100. We know how they rated themselves, how left they are, but we don't have enough data to do anything with the analysis, to actually analyze this, because out of the 20 participants, so some of them moved, so it's we already have 17 participants. So we don't have enough data, but I think it's a great question, and I would have loved to have the answer for it, but it was just not possible.
Cool. All right, next question is from Yunze. I will ask also. So I wonder how you interpret the classifier results in project 2. if I understand correctly, this is not a multivariate classification of the voxels,
Right?
but rather asking at each voxel, does it consistently across subject is consistently across subjects more likely to respond to cheating or paranoia or vice versa?
Okay.
So isn't it going to be very similar as just doing a univariate contrast between groups?
Okay. So the answer is no, it's not similar to univariate, because what you do, so in MVPA, you look at the pattern, in the spatial pattern. And you can think of this classification as a temporal pattern. Okay, so you have a time course, and what you do, you measure based on how similar this time course in time to the mean response. And if you'll do univariate, you'll just average all the time course into one time point, and then you don't have any information in it. Okay, so it's not the same as univariate. And yeah, so if there's another question about this, I can continue, but
yeah, no, I think that was clear. But yeah, if there are more questions, please ask. Next question: why do you think there is more synchronized responses in the brains of right wing versus left wing? Does this difference say something about the yeah, that's what I thought that too. Does this difference say something about the uniformity of thought amongst right wingers? But again, that's a delicate.
yeah, that's a delicate question that I don't want to get into, but I think it's a really good one. I mean, first I want to. So as I said, this is very preliminary, and first what we're doing now is making sure that, okay, so there is you can find a higher inter-subject correlation in one group than the other, but it could be that in both cases, the inter-subject correlation is low. Okay, it doesn't pass a certain threshold. And then it's not very interesting, right? Because it could be that both are not involved in processing the stimuli. It's just by chance, there's a difference between them. But it's a different thing if one is involved and one is not involved. And so that's what we're doing right now, okay? So anything I'm saying, you have to take it with a grain of salt, because we're still making sure that these voxels passed a certain threshold. But I agree with you. I mean, I think your interpretation might be right. It's just an interpretation, because we can also look at their behavioral scores. I can say that the one inside the scanner, they did have more variance than less variance than the left-wing participants. Okay, so in terms of how much they agreed or how emotionally engaged, but we should look better in the behavioral results. Maybe we can find there something about that they were more uniform in their way they interpret things.
Yeah. Cool. Thanks. And the last question. Does the so-called geometry differ between right and left-wing participants, and could this explain differences, for example, in primary auditory cortex? I think Heschel's gyrus can be split into two in some subjects, and I seem to remember that this predicts character traits like being good at science. Seems like these kind of seems like these kind of traits might differ between right and left wing. I think similar arguments could be made about the cingulate cortex, for example, number of paracingulate sulci.
Okay, so I'm not familiar with the study you mentioned about the Eschel gyrus and the traits. I think here, so the intercepted correlation, I think it has many advantages, but it also have some disadvantages. And one of them is that if you find a high correlation, you can say, cool, these regions are involved in processing the stimulus. But if you have low correlation, you're not sure if it's because just this region is not involved, or it's a specific voxel that moved from participants to participant, and that's why I would not like to claim anything about a division in the Eschel gyrus, where it could be that it's just, I prefer looking at larger brain regions, not to say anything about a few voxels, because it could be a result of just different location in different participants, which has nothing to do with their political views.
But I guess the question is whether maybe you can do some kind of Solgal geometry, like Solgus geometry analysis, to try to test, are there differences between the two groups? And if there are, then that might inform some result, like maybe that's something to work with or something like that.
Yeah, there is some work about anatomy that is different between right wing and left wing, like gray matter volume. But again, I don't want to go there, because I think it's not about anatomy, it's about functionality.
And Tim is asking a follow-up question. He was thinking about the findings in early auditory cortex, but they differ. Could this just
anatomy? Yeah, I see it. Okay, so I wonder, what do you mean by just anatomy? That the anatomy differs between left wing and right wing?
I think so. Yeah.
Okay. I don't know. I assume that there's not supposed to be any difference, but we can check this. We can compare this, but also what we're doing to test whether, for example, a classification accuracy is significant or not, is shuffling the left and right wing participants to create two pseudo groups. And we're doing it like 100,000 times. And I think there's no reason to assume that only these 20 participants and have a certain anatomy and the others don't. I don't know. I mean, it seems like a much stronger claim that at the moment I won't claim it.
Yeah. Okay, great. Cool. I think that was our last question. So thanks a lot, and that was a really fascinating talk. And sorry for all the technical troubles in the beginning. They were probably all my fault. Cool. And thanks everybody for joining. And I'm going to end the broadcast now. And there's some applause in the chat. So,
thank you.
Anticlimactic. All right.
Thanks.
Bye, everyone. Cheers.
Bye-bye.